So let's look at the fifth way to consider natural transformation, which are transformation between functors. Let's start with two functors with different domain, f and g. This will lead us to some general construction that we might reuse later. So the simplest functors, a functor is just a drawing of a category A or B within another category X. And so the simplest kind of drawing that we can have is drawing from the category 1. So such a drawing really just amounts to selecting one object within X. Here we call that little x and little y. So what kind of trajectory could there be between two objects x and y within X? Well, it will be, a morphism in X, if it exists. And the notion of transformation between two functors is an indexed version of that. That is, instead of having a category 1, we have a category of index A and B, which have objects and morphism between them. So let's consider all such transformation between those drawings, those indexed collections. And we can build this category F over G, the comma category of F over G, whose objects are the index version of this simple path in X. So it would be a triple A, B, the index, and some path from F of A to G of B within X. So that's a triple of things. And between two such triples, we will consider pairs of morphism, U and V. U is a morphism in A, V is a morphism in B, with the additional property that if we transport U and V within X by F and G, the square will commute here. That is, it doesn't matter which direction we take, it defines a common morphism from F of A to G of B prime. So this commutation is essential. And if we want to define a category, we furthermore need to define identities and composition. So this pair of morphism in A and B, 1A and 1B, is indeed an identity by functoriality, because F will transport the identity of A to the identity of F of A, and likewise for the identity of F of B. So the square will commute, and composition verifies all the associativity condition and the fact that identity is the identity for this composition. So all in all, we've defined the objects, we've defined the morphism, the identities, the composition, and we can verify that it's indeed a category. So it's a category of all the paths from F to G. Now, if we go back to our original problem, which is about natural transformation, we are given two functors, F and G, from a common category A. If we apply this construction that we've discussed, and we explicit F over G, the objects are triples A, B, and F of A to G of B, and here the index A and B are within the category big A, and the morphisms are pairs of morphism U and V, still in A, in the category A, such that the square commutes. Okay, so if we have a natural transformation alpha, what do we have? If you remind the original definition, for each object A of the category big A, we have a morphism F from F of A to G of A, which we call alpha A. And Likewise, if we start from A prime, we have this morphism Fa prime to Ga prime. And for any morphism U from A to A prime, the square Gu alpha A or alpha A prime Fu commutes. That's by definition of a natural transformation. So the fact that it commutes means that this morphism UU is a morphism in F over G. So, and if that's a morphism in F over G, it means we've transported objects of A to object of F over J, and morphisms of A to morphisms in F over J. So we've actually defined a functor. And naturality is the same as saying that we have a functor. Now, this functor has alpha bar has the extra property that if we start from F over G and just consider the first component of the triples, so that would give us a functor D. Or if we consider the last component of this triple, which will give ourselves a functor C, this alpha bar commutes. If we do D compose with alpha bar, it will give us the identity on A, and if we do C compose with alpha bar, it will give us the identity of over A. Or said otherwise, if we compose D cross C with alpha bar, we get the functor delta, which to any objects A associates A cross A. So it's a functor from A to the product category A cross A. So a natural transformation will give us such a functor, and conversely, such a functor will give us a natural transformation. So this commutation just says that, if we start from the object A, we go to an object in F over J, where each component, the first component and the last component of this triple will be A, which is part of a natural transformation definition. Now that's one way to see things, but here we're going from objects of A to arrows in B, and we might wonder, is there a more primitive move that will allow us to do that in 2 steps, which would allow us to map arrows of A to arrows of B, every arrow of A to some arrow of B. And indeed there is. If we consider this category A over A, or more precisely the comma category of the functor, identity functor 1A over 1A, the objects are those triple A, B, and U, A prime, B prime, V, and the arrows between such 2 objects will be pairs of morphisms in A, F and G, such that the square commutes GU and VF. Now we see that we can build a functor alpha tilde when we associate to each element of A over A, that is to each U, we associate the common value, which would be G of U alpha A or alpha B F of U, and to any other object V, we associate again the common value alpha tilde V, which denotes either GV alpha A prime or alpha B prime F of V. And to arrows FG between the object U and V of A over A, we associate the morphism, the pair of morphism FG, which is the morphism of F over G. Now we have a question: does this central square commute? And indeed, we can check that it does. And the fact that it does means that it's indeed the pair FG is indeed an arrow of f over g, because that's part of the definition of being an arrow in that category. And we can go through this, and I'll let you look at by your own. But it's really trivial. Now, how do we recover the first transformation alpha bar that we had? Well, we see that if we precompose alpha tilde by the identity functor, which to every object of A associate the object of A square or A over A, which is the identity morphism at this object, if we precompose alpha bar by such a functor, we get alpha tilde by such a functor, we get alpha bar. And whereas previously we had this commutation A delta alpha bar C cross D, here we have this commutation C cross D alpha tilde, and the identity over the product category A cross A and C cross D. And so C cross D they are doing the same thing, but they are applied at different domain category, either A over A or F over G, a different comma category. And that's more primitive in a way, because from alpha tilde we just stick this identity functor, which always exists in any category, because any object has an identity morphism. That's part of the axiom of category. And so we stick this for free functor, and we get back this alpha tilde. So in a way, alpha bar, we get back this alpha bar. So in a way, alpha tilde is more more functorial in a way, I would say. And so that concludes our fifth characterization of natural transformation, which is another way to look at it and get an intuition over it.